You are a pilot of a giant robot called a Jaeger. When it moves, there are tens of thousands of tons of steel and composite materials under you. Control doesn't run through levers. It runs through a neural link. The system reads electrical activity from the cortex, vestibular signals, and transfers them into actuator commands. Every movement you make, it repeats. Every mistake, it mirrors. A Jaeger can't be operated by one person. The human brain can't handle the full data flow from sensors and the motor control load. That's why there are two pilots. One handles the right hemisphere of control, the other the left. The drift link synchronizes both consciousnesses, merging their motor impulses and memories into a single control profile. Average latency between pilots is 0.2 seconds. If it rises, command signals desynchronize and the machine begins to lose coordination. Each Jaeger is an extreme cost platform. Construction, weapons integration, training infrastructure, and logistics raise the full program cost per unit to roughly $100 billion. That figure includes reactor assembly, high-density alloys, neural link fabrication, test runs, and ocean transport systems. For reference, one SpaceX Starship costs about $200 million to build and launch, while the entire Starlink constellation of 5,000+ satellites has a total deployment cost near $10 billion. At $100 billion per Jaeger, the same budget could fund around 500 Starships or the entire Starlink network times 10. Gypsy Danger, USA, height about 260 feet tall, mass 25,075 tons. Two pilots. The reactor provides long-term autonomy but generates excess heat. Cockpit temperature under load reaches 120 degrees Fahrenheit. Top speed on land, 25 miles per hour. Stable in water up to 250 feet tall deep. If one pilot disconnects or blacks out, the system switches to emergency mode with limited mobility. An older Mark III analog model, immune to EMP, requires constant thermal management and precise movement synchronization. After more than 3 minutes of continuous combat, the system automatically lowers output to prevent overheating. Striker Eureka, Australia, height about 250 feet tall, mass 19,071 tons. Two pilots. Maximum ground speed 30 to 35 miles per hour. Command response is nearly instant. Power consumption is high. Cooling capacity limited. Designed for short attack bursts and quick retreats. On uneven terrain requires continuous step correction. At speeds above 30 miles per hour, leg stress rises sharply. After every mission, locking clamps and hydraulic lines must be checked. During heavy rain or strong wind, speed should be reduced by 20% to maintain stability. Crimson Typhoon, China. Height about 250 feet tall. Mass 19,937 tons. Three pilots. Triple arm configuration increases maneuverability, but requires perfect synchronization. If one pilot is lost, the third arm switches to semi-automatic control. Average speed 20 to 22 miles per hour. Optimized for close quarters combat and rapid strikes. If one arm or one pilot fails, efficiency drops by up to 40%. The three-pilot drift link demands strict control. Emotional spikes from one pilot can disrupt all others. Cherno Alpha, Russia. Height about 280 feet tall, mass 41,000 tons. Two pilots, oldest active model, slow speed, 12 to 15 miles per hour, but armor can withstand direct hits from Category 4 Kaiju. Highly stable, capable of 25-degree tilt without loss of balance. Designed for frontline containment and heavy impact combat. Main tactic, absorb impact with the body. Holding a static stance for over 40 seconds overheats knee joints. Retreat required. Arm weapons are designed for short engagements, no more than 10 strikes per sequence. Coyote Tango, Japan. Height about 280 feet tall, mass 28,700 tons. Two pilots. An artillery platform equipped with twin spinal-mounted cannons. Average movement speed 14 to 16 miles per hour. Requires solid ground and short firing bursts. After 3 consecutive shots, barrel pressure exceeds safety limits. Reload time, 15 to 20 seconds. On soft terrain, the frame sinks about 1 foot, shifting the firing angle. Urban deployment requires pre-calculated positioning. Tacit Ronin, Japan. Height about 244 feet tall, mass 14,200 tons. Two pilots. Light, agile melee model, speed 22 to 24 miles per hour. Thin armor, designed for evasion, not blocking. Operates in short, fast strike sequences. Arm joints overheat after 1 minute of continuous fighting. After every engagement, cooling and blade inspection are mandatory. Weak in frontal collisions, especially against heavier opponents. Horizon Brave, China. Height about 238 feet tall, mass 18,500 tons. Two pilots. Balanced early generation model for defensive missions. Speed 16 to 18 miles per hour. Low center of gravity makes it resistant to wind and waves. Used primarily as a defensive unit. Performs well in close-range encounters but vulnerable to top-down attacks. Requires support from faster Jaegers for aerial threats. All digital control models lose function after strong EMP exposure. Analog systems like Gypsy Danger remain operational. After an EMP, system reboot must occur within 20 seconds before automatic circuit lockdown. Kaiju blood is toxic and corrosive. Corrosion starts 5 minutes after exposure. Post-mission, the frame must undergo full decontamination with neutralizing agents. Ignoring the process leads to joint failure within 1 shift. Optimal combat depth, up to 250 feet tall. Deeper pressure affects hydraulic lines. Waves higher than 15 feet tall reduce stability. Cherno and Coyote perform best due to higher mass and center balance. A 30-foot tall fall generates 12 to 15 grams of impact force in the cockpit. Loss of consciousness possible after 2 to 3 seconds. Breathing technique mitigates the effect. After landing, automatic dampers absorb residual motion. Melee weapons activate only after target lock. Incorrect attack angle reduces efficiency and causes recoil. Gypsy and Tacit have the most precise stabilization systems. Cherno is not designed for bladed weapons. After each battle, actuator and joint seals must be inspected and replaced if needed. Full service cycle, 8 to 12 hours. Skipping maintenance leads to step imbalance and joint failure within a few missions. Lighters operate normally in rain, but wet concrete reduces traction. Striker loses about 20% of ground speed. Cherno is barely affected. Wind above 50 miles per hour lowers strike accuracy by a third. Movement is prohibited during thunderstorms. Lightning targets sensor arrays. Below -10 degrees Fahrenheit, coolant viscosity increases and pressure drops. On ice, foot slippage occurs even after a 1-foot tall step. Cherno and Horizon remain most stable due to weight and frame width. Signal delay between brain and actuators, 30 to 40 milliseconds. Uncontrolled thoughts create micro-movements. Pilots are trained to think briefly and without emotion. Any mental distraction directly affects control precision. Ejection requires at least 150 feet tall of vertical clearance. In cities or during storms, it's rarely possible. If the Jaeger falls on its side, the capsule locks. Pilots switch to defensive standby mode. Limb destruction is automatically detected. Average repair time, 40 hours per damaged limb. Armor cracks acceptable up to 0.5 inch. Joint deformation over 2 millimeters requires full replacement. If one pilot loses consciousness, the other feels drift desync in 0.3 seconds. Emergency mode maintains motion for up to 40 seconds. Then the system halts to prevent neural damage. Continuing combat alone is impossible. After 1 hour of active operation, concentration decreases. Average heart rate, 150 beats per minute. Dehydration occurs rapidly. The cooling suit compensates partially. After every shift, pilots undergo medical evaluation. The working, operational mass of a Jaeger is routinely several times higher than its catalog figure once you account for structural reinforcements, internal systems, and fuel consumables. In practice, a cockpit input error or a millisecond of control lag scales up. A tiny misalignment in the link can redirect thousands of tons of force. Operational mass can be on the order of 2 to 10 times the nominal number, depending on fit-out and payload. For a pilot, that means any desync or delay isn't theoretical. It multiplies into real massive loads the actuators must correct instantly. The con pod is the real vulnerability in a Jaeger. The crew access hatch sits inside the torso, and the access tunnels lead straight to the neural link mount. If that section is hit, it doesn't just endanger the pilots, it risks a full shutdown because the neural link hardware, escape hatches, and primary sensor arrays are co-located. Your safe area inside the machine is the con pod itself. A compact, exposed compartment, not the broad bulk of the hull. Damage to that small zone compromises the entire control chain. A Jaeger pilot works under constant heat and G-forces. One wrong command can cost millions of dollars and hundreds of lives. A Jaeger moves only while the pilots stay connected. Without them, it's just metal.